Logic is underpinning of all reasoned arguments, and the logic has been studied for sort of history of civilization in some sense. It was studied by Greeks because they understood the role of mathematics and philosophy. It was studied extensively there. Aristotle wrote the first systematic treatise of logic, and his work had significant influence in throughout. But because his work was still based on ordinary language, it had issues, the same kind of issues that we would have with English today. The logic that we study in this class, the formalization of that started somewhere around 17th century. In 19th century, that is around in 1847, Boole and De Morgan published these papers on mathematical analysis of logic and formal logic, and that sort of got us into thinking that mathematics is not just about numbers, but it's about a lot of these other things. And one of the things that came out of this is Boolean logic, and that's what we are going to study today. Since Boole and De Morgan, logic and mathematics have been linked together. So when people talk about mathematics and logic, it's often used interchangeably, and I will be doing the same thing throughout this class as well. Logic is part of mathematics, but at the same time, it is the language of mathematics. It's the way we are going to describe mathematical results in almost every area of mathematics. In the late 19th and early 20th century, it was believed that all of the mathematics could be reduced to symbolic logic and made purely formal. In other words, whatever result is true, we could somehow discuss it in logic, and we would be able to quote unquote prove it in that logic as well. It turned out that this belief was wrong, and we have to modify that belief today, because in 1930s Gödel proved this result that said that whenever the logic is strong enough, whenever your axioms are strong enough, you are going to have certain statements that are true, but you will not be able to prove those statements as being true. So essentially what he showed was there would always be statements such that the truths of those statements cannot be derived in the formal system that we have. The study of logic is usually broken into several parts. The first and most fundamental part that we are going to study is the part we are going to study today, called propositional logic, and subsequently we will introduce predicate logic about 3 weeks from now, which is the language of mathematics. Okay, so the thing that we are going to define now is the notion of a proposition that forms the basis of all propositional logic. Proposition is an unambiguous declarative statement that is either true or false. So let's look at what each of the term means. It needs to be unambiguous. It should have a clear meaning of what we're talking about. It has to be a declarative statement. Essentially, a declarative statement, if you think about your first grade English, it's basically the statement that ends with a period at the end, not a question mark, not an exclamation mark, nothing else. It ends with a period at the end, and the statement should be either true or false. It's important to note that the proposition does not have to be true. It can be false. So the proposition has two truth values. The there is a truth value equal true, there is a truth value equal false. Okay, so let's look at which of these are propositions and what are their truth values. Remember, a proposition is an unambiguous declarative statement that is either true or false. So let's look at the first statement. The first statement is 2 plus 2 equal to 4. So let's ask this question. Is it unambiguous? Yes, we know what 2 is, we know what plus is, we know what 4 is. 2 plus 2 equals 4. We know exactly what it means. It's unambiguous. The statement is either true or false. And yes, in fact, the statement is true, so it's a proposition. Its truth value is true. 1 is equal to 0. Is this a proposition? Once again, let's look at what we have. Is it unambiguous? The answer is yes. Is it declarative? Yes. And is it true or false? Yes, it is in fact false. It will rain tomorrow. Is this unambiguous? Yes, we know what rain means, we know what tomorrow means. Is it declarative? Yes, it is declarative. Is it true or false? Well, we don't know it right now, we will know it tomorrow. Now we can use this. So we don't know the truth value of this right now, but we can use it in terms of things like, if it rains tomorrow, then the ground will be wet tomorrow. So we can use these propositions for these kinds of things. Go green. This is not a proposition. The number 5. Again, this is not a proposition. What I want you to be able to do with this slide is I want you to understand why each of this is a proposition or not a proposition, and to be able to decide whether something is a proposition or not if you are given the corresponding statement. So here are some examples of non-propositions. So as I said, we want propositions to be declarative statements. So if it's something else, it's not a proposition. Exclamations are not propositions. Questions are not propositions. If I have a statement that is ambiguous, I don't know what that means. Sentences containing things like I, he, there, etc. are going to be non-propositions. Another important thing is statements that refer to themselves are not going to be propositions. There is a reasoning behind that, but I'm not going to get into why that is so. But statements like this statement is false is not a proposition. Okay, so this is some review material for you. You are given a bunch of statements. You need to figure out which of these are propositions, which of them are not propositions, and why. And this is the last thing. This is not really related to the class as much, but I want you to think about, I'm going to give you a proof. Figure out where the mistake in this proof is. So what I'm going to prove to you, I'm going to tell you upfront before you see anything, is I'm going to prove that 1 meter is equal to 1 centimeter. Of course, I must be doing something wrong because clearly 1 centimeter is not the same as 1 meter. So I want you to figure out what the mistake is. So I start with 1 meter. Then I'm going to say this is equal to 10 centimeters times 10 centimeters. Continue further. It's 1/10 of a meter times 1/10 of a meter. That is 1/100th of a meter, and which is same as 1 centimeter. So your job is to figure out where the mistake is. Clearly there is a mistake. Don't say that the mistake is 1 meter is not equal to 1 centimeter, because if there is a mistake, you need to tell me where I made a mistake. So the mistake could be between 1 to 2, it could be between 2 to 3, it could be between 3 to 4, it could be between 4 to 5. Your job is to figure out where the mistake is, and this is something that I will talk about in the class as well. So this is what I wanted to check before you go ahead. A couple of slides back we had some statements, and the question was which of these are propositions and which are not. If you have understood it, wonderful. If not, I want you to go ahead, review it again and ask questions. If you have something that you didn't understand, please ask questions about that. I want to make one important note. What we are learning is a language of logic. This means that treat it like a new language. So if you were learning a new language, say you were in high school and you are learning Spanish, French, which is what many of you may have done, or if English is not your primary language, then you may have learned English as another language. You need to spend some time figuring out how the syntax of it works. How do you sort of put things together so that whatever is said is meaningful? We will need to do something very similar to that in this case. So that means that if I think of this as a brand new language, then whatever you'll need to learn, that would be vocabulary, syntax, we will need to do the same thing here, and we need to be quite precise in doing that, because at the end of the day we want to feed this to computers who will understand only what is spoken, what is given to them. Unlike a native speaker of, say, Spanish would understand something even if you don't say it in the right words, computers will not. And that's why it's important that we get this right. And that's why we're going to spend some time going over the syntax of this language of logic and how to interpret it, what it means, and so on. Now we have reached the end of the module, and at the end of every module you would have a review quiz that will be available in D2L. It could be a quiz directly in D2L, or it might require you to use Connect of the McGraw-Hill associated with your book. Please complete this quiz before we discuss this in class.